Welcome to the Intersecting Us podcast, where math and life intersect.
In this podcast, Brian and Dave explore how math relates to music. From leaf colors to sound creation, math's influence on harmony, frequencies, and more.
Today on the podcast, we're going to go a little bit different direction, take you into some more interesting things about math. This is Brian. We're continuing on our series, which kind of revolves around the Eternity series. We've talked about sunlight. We've talked about the natural log and how that works. And today we're going to go a little different direction to something that I think will probably resonate with everybody looking at music. Dave, you want to start us out there and kind of segue into that subject?
Sure. Well, welcome everybody. It's always a pleasure to be here. And, I always enjoy when I find what we talk about kind of like connects to my day-to-day living. And just yesterday, I was in the car with my wife and we were looking at trees. Actually, she was looking at trees. I was probably thinking of some math equation. I don't know. But she said, Dave, do you know why the leaves of the tree change colors? And so, we're from Iowa and, Brian, I don't know if you have any idea why the leaves change color, generally in the fall. But do you have any thoughts on that?
Well, if I remember, I can't remember the name, it's chloroform or chloro something that gives the green. And then when it gets colder or starts to die, that goes away. Mm-hmm. Something like that. It might be more complicated.
Yeah.
You think of something?
I know nothing about this, so all I'm doing is repeating what she said. But, we always think it's like, okay, it's autumn when the weather gets cooler is when the leaves change to a different color. And it's kind of related to that, but it's actually directly related to our first topic, and that is the number of sunlight of hours we get in a day. And so the peak of that is, the first day of summer in like June 22nd or give or take. And that's when the process begins of the number of hours of the day getting shorter. And so that right away impacts the leaves, even though the heat of the summer usually doesn't occur until like maybe late July, early August. It's not the heat that impacts the leaf color. It's the number of hours of sunlight. And so, lo and behold, that little math formula we got with the sine curve now helps me understand why the color of leaves are changing when they do. So, hey, that's just a free bit of trivia that we get at Intersecting Us.
Yeah, no extra charge there.
No extra charge, although if you want to tip us, do you have a tip jar, Brian?
Not yet, but we're working on it.
Okay, let's work on that tip jar.
Virtual tip jar, I think.
So, today we're going to talk about music. And, to kind of think about this, it's like, okay, what is music?
Here, Brian and Dave discuss the harmonic dance, math, music, and the symphony of chimes.
Music is something we hear. We all enjoy it. But one thing that is kind of interesting is how much do we see music? And I play the piano a little bit. And so I, look at the piano keyboard, and that's kind of how I used to think of music. And, there's white keys, there's black keys. So I'll play a different key and that'll play a different sound. And so that is kind of my visual idea of what music is like. But, all those keys look the same other than black and white. And so it doesn't really give me a good feel for like what music looks like. Now, I don't know, Brian, do you have any idea of like what music looks like to you?
Well, I think when you say what music looks like, I think for most of it, my first thought, that's not the way I would, it's like, what does it sound like? Is
right.
And so the way it looks, I guess you're more talking about the things that make the music and what it looks like and how we use them.
Yeah. So most instruments, like a piano, there's the strings and stuff under the hood, literally. But what we as users see has been converted to keys. And so today we're going to talk about chimes, and many of us own chimes, and we own a set, and they're in our backyard. And that's kind of like simplifies music down to literally the length of the chime, and I can see that the notes that come from the chime come from different lengths of chimes. Now, I may not have any clue as to how and why, but at least I can now see something physical that connects length to music. And so that was something I hadn't given much thought about before, but I don't know, I thought that was kind of cool.
Yeah, you make instruments of any kind. I think about I play guitar, and even the way, you're creating something, you're creating an instrument to make the music, and how you do that makes a difference. And you have to be precise. Obviously, if you don't do it right, you don't make the guitar in this case, and you're talking about chimes, wrong lengths, wrong thickness of wrong material, it can make everything sound different. And so you got to be pretty precise at it, which I suppose brings some math into it.
It does. And really everything comes down to the simple idea of a wavelength. And we probably know that when we speak, we're speaking that, it's through waves. And it's the length of the wave that determines like how deep or how high pitch that is, which is the frequency. And so we're going to like jump into that, but all that's connected to a sine curve. And a sine curve, if you remember maybe back in high school math, it does a full complete cycle after the generic sine curve would be after 2 pi units is when it starts kind of at 0 and then it curves its way up to 1. Then it comes back down to 0. That's only half the curve because then it's got to go back down and then it comes back up again. That is one cycle. And that would be a frequency of 1 because it completed one cycle. And then the length of time or the width of that curve on the x-axis then becomes your wavelength. And again, the standard one is that the sine curve has a length of 2 pi. And so there's one frequency every 2 pi length. And, that's connected to a wave, and that's connected also to the speed of sound, because there's a really cool formula, which I didn't really know until this weekend when I was brushing up on all this stuff. Maybe I heard it before, but there's a formula in there that says the frequency times the wavelength equals the speed of sound. And so there's like this constant out there. Now, why that occurs, Brian, help me out. Why does that occur?
The frequency times the wavelength.
Yeah.
Well, I think look at it like a ripple in a water. You think if how often that ripple goes and how long the ripples are between each other, which would be like a sine curve, would make a difference on how quick it got somewhere.
Right.
And so it's a pretty good analogy of how fast you can get something from one place to another. And,
right.
And those would be, I guess, inversely proportional to some extent,
Yeah.
Yeah.
But, it's so cool is that like when we speak, there's a universal speed that sound travels when it goes from my mouth to your ear. And it's not like something that may vary depending upon where I'm at in the, kind of like where I'm at that particular moment. But there's this universal constant out there that's a pattern that we have been able to uncover in nature that I think is underappreciated.
Yeah, I think isn't it? Again, you get the geeky part where sometimes, math people, we remember the numbers and the formulas, but we don't necessarily remember why. And that's, is it like 760 some miles an hour or something like that? Because I think, we got our airplanes that always go under that, the commercial airplanes, because you don't want that boom sound.
Right. Yeah. I just saw it this weekend, and it was something in terms of so many meters per second.
Okay.
The idea that there's some limit out there that all this is based on. And so if you think about that, that's like a number given to us from nature. It's like a constant coming down from the heavens that we have no input into. It's been there since the beginning of time, and it will stay constant. So that number is fixed. And then if you think about the wavelength, you talked about the different instruments. The wavelength we have control over, depending upon, let's say, what instrument you play. You could play a clarinet, you could play a flute. Those have different wavelengths. And also what determines the wavelength is whether there's one hole at the end or two holes at the end. All that determines the wavelength. But if you just think about it, we can manufacture the wavelength based upon the instrument that we create. And so there's three numbers in this equation. There's the speed of sound, there's the wavelength, and the frequency. We can't change the speed of sound. We can impact the wavelength. And then once we do that, all of a sudden now what we've generated is pitch or the frequency. And so that's how we can now create music of different pitch, is simply by changing the wavelength. And so you said you play guitar as you strum different strings. There's different tensions on those strings, and you put your hand on it to impact the wavelength. And so all those things impact the wavelength. Once you determine the wavelength, then the frequency is the sound that comes out of that.
And I do think when this is, as you were talking about that, this kind of has an interesting concept with the whole thing that we're doing with Intersecting Us, the math and the life. And obviously music is one that will probably hit a number of times, not just today, but you think about there are people who are really worried about the math of it or the creation part of it. You know, when somebody's playing, a guitar or a piano, or they may or may not know the math behind it. Mm-hmm. It doesn't, really might not even matter to them, but it does matter if it didn't matter to the person who created the instrument, it wouldn't sound right.
Right.
And so I think there's that applied kind of idea, and then maybe to the beauty and the joy part of it. You don't have to know all this to have joy from listening to music. But those of us who kind of like the behind the scenes, can even maybe get some joy in how to do that, how to create these instruments, or in this case, chimes, which are kind of like instruments, I guess. They're kind of more free flowing, to get music and we know the difference. And when you get into the chimes here in a little bit, your ear, unless you're tone deaf, which is obviously a problem, because that's why they call it that, you can tell the difference if something's off.
Right.
Most people can, some people more than others. But if you hear something off key, it's like it's somebody taking their fingernails on a chalkboard. And
right. And so, math is patterns. And if I'm going to use a piano, that's what I'm used to. But if you look at a piano, you can quickly see a pattern. If you first notice, like the black keys, they go in orders of 2 together, and then there's 3 together, and then it repeats as 2 together. And between that cycle of 2 blacks and 3 blacks, there's 7 white keys. And so that full cycle is 12 keys. And what that means is there's 12 keys to an octave. And if you've ever heard of the note, let's say a C or a D, as you go from one octave to another, you repeat those letters. And so from a C4 to a C5, as they define it, that is a 1 octave difference. And from a D4 to D5 is a 1 octave difference. But there's 12 keys in between that octave. And so before we talked about the idea that the speed of sound is something we humans have no control over. And so here's another question for you to think about that I don't think people think about too often are the definitions of an octave, 12 keys to an octave, is that something that we as humans defined, or is that something like the speed of sound that was given to us?
The next topic of discussion is the mathematical heartbeat of music, exploring octaves and frequencies.
Because I've never questioned the fact that there are 12 notes to an octave. And so without me thinking about it, I would have thought that since the beginning of cave people, we had 12 notes to an octave. And that's the way it came down from just, the speed of sound, the same thing. But what do you think about that, Brian? Do you have any opinions on whether the octaves are human inventions or are they given to us from nature?
Well, so you're kind of asking whether this is something we create or discover, right?
Exactly.
I mean,
Yes.
it's already there, or something that's that we say, well, here are different ways to split this up, and we're going to do 12.
Right.
I guess my first inclination is to think that it's something we split up, but as I try to think about that deeply, I'm not quite sure. It seems like, could you make 8, 24, I don't know, whatever number you want. I guess my first inclination is like, it's how we would split them out. Tell me more. Am I right?
You are. Yeah. And it is incredibly connected to the world of actuarial science.
Oh, cool.
Which is, you and I is like, wow, are you kidding me? Do you mean what I've learned as an actuary? And so as an actuary, you got to think about this equation, y equals 2 raised to the power of x. And so x represents one octave. Now, if you look at x represent each key, then you're going to want to change that exponent. Instead of x, you want it to be x divided by 12. And so let's think about x as each key, and that makes our formula a little bit more involved. But the formula now becomes y equals 2 raised to the quantity x over 12. And so as x increases by one key, then what that tells you is how much the pitch or the frequency will increase as you increase each key. And so, first of all, if we look at simple math, if we go from one octave to another, then we increase x by 12. And so that means that we're going to double our frequency every octave. Okay. Because if you start out, let's say x equals 0, then that gives you 2 raised to the 0 over x, and that's 1. So that's like a starting value. And then as you go 12 more keys, then you get 2 raised to the 1 power. And then you go 12 more keys to 24. Then you get 2 raised to 24 over 12, which is 2. And so now it's gone from 1 to 2 to 4. So there's this doubling impact every octave of the frequency as you go through. And so you can think about that as money doubling with interest. And ironically, as the math gods made it, 12, the number of keys to an octave, also happens to be the number of months in a year. No connection there at all. But it makes it really nice because we can think of money doubling every year as the same as growing with interest once a month. How big is that fund? Knowing that after 1 year, it's going to go from 1 to 2. After 2 years, it's going to go from 2 to 4. But we could also think about, well, where is it after each month? And then that gives us how the frequency increases for each key as we connect the keys to a month. And so let's say you take a piano keyboard and you start at middle C, and then you go on the octave from left to right. Every next key would be like going 1 month in a calendar year. And the math that we use to accumulate money with interest is the same formula, y equals 2 to the x, that we use to determine the frequency. Isn't that cool?
Yeah, well, it is. And one thing that came to mind, and I don't know if this would apply, but when you tune a guitar, I mean, the way to do it now, some people do it by ear, as they say, but, someone being able to, you hear a C and you know it's a C. Some people can do that, some people can't. But what I have is this little electronic tuner, and you put it on, 6 strings on the guitars, and you put it on the first one, the G, and you pluck the string, and then that little device, which is only like $15-$20, this little thing with that bit of battery in it, it'll show you, do you need to tighten that string or loosen that string to get the frequency, get it different. But in my mind, I was thinking, how does it know? How does it know that's a G and not a F? You know, how does that little box know that? And I wonder if it has something to do with what you just said. That they get like a core sound and then they're just going from one to the other based on a formula.
Right.
It's just a little computer, really, is all it is.
Right. Now, as a side note, as you bring that up, this is what I've read is that there are tools that they can use to tune a piano that are like extremely accurate to get the math the way you want it to work. Unfortunately, for those that are musically gifted, that perfect tuning actually is not what they want because it's almost too perfect. And a trained musician is going to want a little bit of style in there where they've got a sound they're trying to replicate that is slightly different than what the perfect math would indicate. And so if you're looking at the best tuners in the world, they're mainly going to be tuning that by ear because they're trying to get a sound that is slightly different. And I mean slightly, it's not like it's very much, it's decimal places, but for the trained musician, they know what they're listening to. And I found that extremely fascinating that there's people with that gift to be able to determine a slight change in the frequency where they get exactly what they want. And they know that this is like better than perfect. It's kind of like the human touch that they're looking for. And so that, I think that's just cool.
Well, it is because we've been talking about, you know, the math and the life, and we're obviously getting into math and the concepts, and here we are in music, but yet also talk about joy and beauty and purpose and meaning and value and truth and all those wonderful things. You know, it is interesting that, you know, a human is, you know, grows up and is able to do something like that. And just, it's almost innate, you know, some are better than others, but I do know, like, when you do that, and I haven't played as much lately, but, and maybe people who are listening with music, you just kind of know when you hit that, when it's the E string and you hit that and it's like, that's the E, you know, I don't have to look at that silly machine. I know that just sounds like it, you know, are much better than others with that. But that ear thing is the thing. And we got about 8-9 minutes left. We talk about a type of chimes that give kind of that pleasant ear thing and the math that goes with that. You maybe want to kind of go into that part coming off of your formula that you talked about before.
Sure. And this comes back to the question I have not answered yet, as far as whether the octaves are discovered or invented. The answer to that is that they've been invented. That is something that we humans have done. And they looked at different options for that. I know one option was they could have chosen 7. And then another option was like a really large number. I think it was 42, but maybe give or take one number in there. Can you imagine a keyboard with 42 keys per octave? That would be a little much. So that one got nixed because it was too many keys per octave. But what made them think of 7, 12, and 42? Well, lo and behold, this comes down to pure math. And if you're an actuary, you can actually think about this because we're going to return to our money doubling again. And what makes music sound really good, this goes way back to Pythagoras, is when things are in integer intervals. And so let's look at a fund where you invest $1 at the beginning of the year. And then in music terms, a sweet spot of that fund is when it grows to 4/3 of the original value. So it goes from 3/3 to 4/3. Okay. So the question is, when during the year does that fund equal 4/3? And if you use 12ths as an indicator, then when you put in 5 for your value of X, so you can punch in your calculator and you get Y equals 2 raised to the 5/12, you are very close to the same result as 4/3. And so the math of that exponential growth hits a month, if you want to think of that way, because the goal is to hit 4/3. So that's one target. another target is you want to hit 5/4, which is 1.25. So the question is, like, at what month do you get a 25% growth where the value of the fund is 5/4? Is there an end of the month of time when that occurs? And the answer is yes. It's after 4 months. And this is not anything that is contrived. This just happens to be the beauty of using 12 as an exponent. And so we can hit 5/4 pretty close. We can hit 4/3 pretty close. And probably most important is the one where we hit 50% growth, which is 3/2. And you think 50% growth, that's going to be like after 6 months, but that's thinking that money grows like simple interest in a linear way. But if you've got exponential growth, you get 50% growth after month 7. Now, none of these hit it exactly, but they are close enough where 12 is your best choice for an octave where you hit all of these values. And so that's why we chose an octave of 12 to be the octave of choice. And that's also the reason why the pentatonic chimes has 5 chimes to it, which is, not all 12. But what it's trying to do is it takes the notes that are in these key integrals. So we would start with, let's say, if we want to do a pentatonic chime using the octave of C, then we would have C as the beginning value. And then we would look for what is the key 4 notes above the C. And then that would be your 25% growth. What is 5 notes above a C? That is 33% growth. What is the note 7 notes above a C? That's 50% growth. And those are 4 of the keys, the chimes that make up the pentatonic chime. And so the reason why the pentatonic chime sounds good is because you've got these integer numbers that are pleasing to the sound that hit this exponential curve. And so that is just, I think, almost too cool to be true, especially realizing how close this ties to money doubling in a fund. And this is the same math that determines how music works and how a chime sounds good, regardless of which notes you play.
And I think that's always such a cool discovery. We've been finding that that's kind of what we're trying to do is think about things deep, look into the deep things. And this is just, it's one of those things that it didn't have to be that way. I mean, it just is. And we probe reasons why maybe, but it's both the math, certainly. But even in that, you said it was really close to 33%, really close. But that goes back to the idea that the perfect, or the best, I guess we would say, tuners are ones that are not quite exactly on, but a little also fits that too. And I guess that gets, and hopefully the audience is thinking that too. This is really neat. I mean, you don't see this in everything, but when you start seeing these things, it's just a discovery that people have found out in the history of humanity. It's like, well, this really makes sense. And it's not only does it fit mathematically, it touches the heart and allows music. I mean, my golly, think how much that changes the world. So we guys got a minute or two left here. Is there anything else you want to kind of sum up with here?
I hadn't thought about this, but I would be open if someone is like one of those music people that we talked about that has that fine tuning ability, that they would like to talk more about that and share this with our audience. You could be a potential guest on our podcast, because I think that it'd be really cool just to hear someone who actually does this, what they're thinking about and why that sounds good, and just give us an insight into what's going on into your mind and into your ears as you're doing that work. So, if you happen to be that person, contact Brian or I, and we'd be glad to, look at getting you in. But I'm going to just kind of finishing up with some simple concepts of, if you look at a chime, which is what we started with, is the idea is like you can look at a chime and you know that one chime is going to play a different sound than another chime. And in the pentatonic chimes, you actually have 6 because the longest one and the shortest one are connected by an octave. And so you get a complete octave in a pentatonic chime. And so one question that you might think about is, why do those 2 chimes make a sound that is an octave apart? And so if we think through the math, we just got done talking about doubling. And the first thought would be, I would anticipate those chimes to be a length that is double apart. So if one chime is length 1, then the other chime would be length 2. And if you look at the chimes from a pentatonic scale and compare the longest with the shortest, they're not double. They're actually closer together. And before we get into that, I'll mention why. What would you expect to sound with a higher pitch? I'll ask you, Brian. Do you expect the longest chime to have a higher pitch or a lower pitch?
I guess it would seem lower, just because when you look on I guess those chime things or xylophones, the smaller ones seem to have the higher note. Yeah.
And, you're right, Brian. My first reaction would be, I think of everything in terms of frequency. So I think of a longer chime is going to have a higher frequency. But the idea that I want you to think about is the length of the chime connects to the wavelength. And so if you make a chime longer, you are making the wavelength longer. And because wavelength and frequency are inversely related, remember, wavelength times frequency equals a constant. By increasing the wavelength, you are decreasing the frequency. And so first of all, let's get the connection that the longer chime produces the lowest pitch, the lowest frequency. So that's one thing. And then the second thing, and I'll kind of end with this, is how can we connect an octave from a chime to the math that we're talking about? And the answer to that was surprising to me, is that we think of it maybe as a 2-to-1 relationship, but it's not one-dimensional that they're related. It's actually the squared area is where they are related. And so what I mean by that is, if you would have one chime, let's say, that has length 1, then 1 squared is 2. Excuse me, 1 squared is 1. And then you want something that is going to connect with that. Well, its square's got to be double that. So its square has to be 2. And so if you want to create 2 chimes that are 1 octave apart, the first chime would be length 1, and then the second chime would be the square root of 2 longer than the first. In other words, that 1 squared is times 2 equals 2 square root of 2 squared. And so you would expect that the longest chime would be the square root of 2 times as long as the shortest chime. And the square root of 2 is like 1.41. So that means the longest chime should be 1.41 longer than the shortest chime. And that's because the square root of 2 is 1.41.
So we're going to get into that a little bit more in future podcasts about that type of thing. And we're always going to be looking into things you discover that are practical, but then get into, beauty and truth and value and joy and all those types of things. On our next podcast, we're going to kind of take this into more of maybe looking at the philosophy of how things are discovered or created, and what that means for not just our day-to-day lives, but some of the beauty of our lives and maybe even the meaning of our lives. So we thank you for listening. This is we're going to continue intersecting math and life as Dave and I kind of continue to have our fireside chats here, talking about things that really matter and hopefully are a little bit fun for you too.
This has been the Intersecting Us podcast. To further engage with Intersecting Us, go to intersectingus.com.